Assalamu alaikum and hello everyone. So for this session, we're going to look at how we want to obtain eigenvalue and eigenvector for a 3-degree of freedom problems. So previously we have looked at 2-degree of freedom, and now we're going to look on how do we obtain the eigenvalue and eigenvector for 3-degree of freedom problem. So let's consider a 3-degree of freedom problem. Okay, so if let's say we have an example like this, whereby this is a 3-degree of freedom. So how do you obtain 3-degree of freedom? Is by multiplying the number of mass multiplied by the direction. Okay, so we have 3 mass and we only have one direction, which is the horizontal direction or x. So 3 multiplied by 1 is 3-degree of freedom. So given that K1 is 3, K2 is 5, and K3 is 4 Newton per meter, and mass 1 is given as 2 kilogram, mass 3 given as 3 kilogram, and mass 3 as 1 kilogram. So first, what you need to do is that you need to develop the equation of motion from free body diagram. You can refer to my other videos that shows you how to develop equation of motion. So from this 3-degree of freedom system, we will have 3 equations, which is first equation is for mass 1, equation 2 is respected to M2, and equation 3 is in respect to mass 3. Okay, so after you have developed the equation of motion, we need to divide it with M. Okay, why we divide with M? So that in the end, matrix M will be converted into identity matrix. So once you divide with M, okay, equation 1 has become equation 4. Equation 2 has become equation 5. And equation 3 has become equation 6. And if you remember, the next step is that what we did was we write it in matrix form. Okay, so it's a 3 by 3 matrix. 2-degree of freedom, you get 2 by 2 matrix. So this is how we convert from this set of equations into matrix form. So what do we do next is that we put in all values into matrix A. So if you realize that this has become our identity matrix, this is our A matrix, okay, and this is, okay, so if I replace all the values, what I will get is that 1, 0, 0, 0, 1, 0, 0, 0, 1, x double dot 1, x double dot 2, x double dot 3, plus, this is where we have replaced value. We put in all the values, we get 4, negative 2.5, 0, negative 1.667. I don't have enough space, so I need to move it forward. Negative 2.5, 0, 3, negative 1.333, 0, negative 4, 4. Okay, so what I did was I put in all values in matrix A, okay, the K1, K2, M1, and everything. And this is x1, x2, and x3 equals to 0. So how do we want to solve this? Because we got x double dot here and x in here. So if you remember the step, what we did was we assume harmonic motion. Where harmonic motion is given by x equals to v sine omega t and x double dot is negative omega squared v sine omega t. So what we did was we replace it in here, and this one we replace it in here. So in the end, once we assume harmonic motion, and once we take out the omega squared, so it has become negative omega squared 1 0 0 0 1 0 0 0 1. This one has become v1, v2, and v3 plus 4, negative 2.5, 0, negative 1.667, 3, negative 1.333, 0, negative 4, 4, v1, v2, and v3. This is equals to 0. So next is that we rearrange so that it will be in the form of a minus lambda I equals to 0. So 4, negative 2.5, 0, negative 1.667, 3, negative 1.333, 0, negative 4, 4, minus lambda 1, 0, 0, 0, 0, 0, 0, 1. Okay, and this is actually, we need to multiply it with v1, v2, and v3 equals to 0. Okay, so since v1, since matrix V cannot be 0, so in the end, we will end up with this one equals to 0. Okay, so negative 2.5, 0, negative 1.667, 3, negative 1.333, 0, negative 4, 4, minus lambda, or maybe I can put lambda in here. Okay, so become lambda 0, 0, 0, lambda 0, 0, 0, lambda goes to 0. So if we combine these two together, simplify it, in the end, we will get 4 minus lambda, negative 2.5, 0, negative 1.667, 3 minus lambda, okay, 3 minus lambda, and negative 1.333, 0, negative 4, 4 minus lambda, and this is equals to 0. Okay, so how do we want to obtain the value of lambda? In 2 degrees of freedom, we use Cramer's rule to get the determinant. But for the 3 degrees of freedom, okay, we need to use Serre's rule. Okay, you can Google on how to use Serre's rule. Okay, from Sarah's rule, okay, so you can refer to any video on Sarah's rule. So basically, this multiply with this and this minus this and this. So we get 4 minus lambda multiply with 3 minus lambda multiply with 4 minus lambda minus negative 4 multiply with negative 1.333. Okay, and then minus this, okay, if you refer to Sarah's rule, minus negative 2.5 that multiply with multiplication of this and this. Okay, so 1.6, sorry, there's negative there. So negative 1.667 multiply with 4 minus lambda minus this multiply with this. So since this multiply with this is equals to 0, so don't need to write that, plus this one multiply with this and this. But since this is 0, 0 you multiply with anything, you got 0, so you don't need to write anything. So it becomes 0, and all of these is equals to 0 here. Okay, so what you need to do now, you expand everything in the bracket. So you got 4 minus lambda, 12 minus 3 lambda minus 4 lambda plus lambda squared minus 5.333. Okay, so this is things that is in the bracket. And since negative and negative we can plus, so we can plus 2.5 multiply, expand the things in the bracket. So it will become negative 6.668 plus 1.667 lambda. This is equals to 0. So next, what you do is that you need to solve things in here, okay, because this and these can be simplified. So 4 minus lambda multiply with lambda squared minus 7 lambda plus 6.667 minus, then you expand this one, 16.67 plus 4.1675 lambda equals to 0. So after this, you need to expand this. It will become 4 lambda squared minus 28 lambda plus 26.668 minus lambda to the power of 3 plus 7 lambda squared minus 6.667 lambda minus 16.67 plus 4.1675 lambda equals to 0. So next we simplify all of this. It becomes negative lambda to the power of 3 plus 11 lambda squared minus 30.4995 lambda plus 9.998 equals to 0. So from here, how do you want to get the roots? Okay, so you can Google. Basically, we can use our scientific calculator. Same goes to 2 degree of freedom. So using scientific calculator, and from the scientific calculator, you will get 3 roots. Okay, but you need to remember. So those roots will represent the lambda. Okay, so some, for example, you might get the first root is higher than the second root and so on. So just make sure when you want to write your answer down, make sure that lambda 1 is smaller than lambda 2 and lambda 2 is smaller than lambda 3. Okay, so if example I got 0.3774, 6.6226 and 4, so rearrange it so that the first lambda is smaller than the second lambda and so on. So lambda 1 from the calculator will get 0.3774. Lambda 2 is equals to 4 and lambda 3 equals to 6.6226. And remember that lambda is actually omega squared. So from the lambda value itself, we can get our omega 1, which is the square root of our lambda. Okay, square root of lambda 1. Give us 0.6143. Omega 2, which is the second natural frequency, is 2. And omega 3 is 2.5734. Remember that the unit for omega is radian per second. Okay, so now we have identified the eigenvalue. Okay, so this is our eigenvalue, all of this, and our natural frequency. So for 3 degree of freedom, we will have 3 eigenvalues, which is lambda 1, lambda 2, and lambda 3. So next, we want to get the eigenvector. Since we have 3 eigenvalues, so eigenvector, we will also obtain 3 eigenvectors. So how can we obtain the eigenvector? If you remember, from 2 degree of freedom, we need to call back this function, this matrix, the A matrix, multiply with matrix V. Okay, so I write back the matrix again. 4 minus lambda. Okay, this is our matrix A, negative 2.5, 0, negative 1.667, 3 minus lambda, negative 1.333, 0, negative 4, 4 minus lambda. So this is our matrix A, and our matrix V is V1, V2, and V3. All of this is equals to 0. So now remember that eigenvector is actually we want to identify the V1, V2, and V3. So how do we want to identify the first eigenvector? Okay, so in order for us to obtain the first eigenvector, we need to use the first eigenvalue where lambda 1 is equals to 0.3774. Okay, so this is our lambda 1. Lambda 1 will give us the first eigenvector. So what we're going to do is that we're going to replace this lambda value into this. So this matrix will become 3.6226, negative 1.667, 0, negative 2.5, 2.6226, negative 4, 0, negative 1.333, 3.6226. Again, this is our A matrix, and V1, V2, V3 goes to 0. So if you remember, in second degree of freedom, in order for us to obtain the value of V1, V2, and V3, what we did was we normalize V1 equals to 1. Okay, so if you look here, in order for us to get the V2 value, we can use the first row, whereby negative 3.6226 V1 multiplied with V1 minus 2.5 V2 plus 0 V3 is equals to 0. And since V3 does not appear in the first row, so it makes things easier, whereby we can get V2 value straight away. So from the first row, 3.6226 multiplied with V1. So remember that V1 is 1 because we normalize it. Minus 2.5 V2 equals to 0. So from here, we can get V2 equals to 1.449. So we already have V1 value and V2 value. So next, how do we want to get V3? So the easiest way is to use the third row. Okay, because why? Because we, in the third row, the only unknown is V2 and V3. So since we already got V2 values, so we can replace it straight away. So I write back from the third row. Okay, from the third row, 0 V1 minus 4 V2. Okay, from the third row, this is already 0, plus 3.6226 V3 equals to 0. So what we're going to do is that we're going to replace the V2 value in here. In the end, you can obtain the V3 value, which is 1.6. So in order for us to get the first eigenvector, to recap, we're going to use the lambda 1 value, replace back in the matrix A, V, okay, use back this matrix, and replace the lambda value, okay, of lambda 1, if we want to find lambda 1. If we want to find eigenvector 1, so replace in this matrix lambda as the lambda 1. And in the end, we can get V1, V2, and V3. So the first eigenvector is V1, which is 1, okay, V2, which is this one, 1.449, and V3, which is this one, 1.6, okay. All right, so that is for the first eigenvector. So how do we obtain the second eigenvector? It's the same thing again. Replace lambda 2 now in this matrix. So in order for us to get a second eigenvector, we need to use the second eigenvalue, which is lambda 2 equals to 4. So if I replace back lambda 2 equals to 4 in this matrix, what will I get is that I'll get 0, negative 1.667, 0, negative 2.5, negative 1, and negative 4, 0, negative 1.333, 0, V1, V2, V3 equals to 0. All right, so remember, 3-degree of freedom, we're going to normalize V1 as 1. Okay, V1 will be 1. So same thing, we use the first row. Okay, but things are a bit easier now because in the first row there will be no V1 and V3 because it's 0. So meaning that 0 V1 minus 2.5 V2 plus 0 V3 equals to 0. So V2 is equals to 0. Okay. Why? Because this will become 0 and this will become 0. Okay. In the lambda one, we use the first row and the last row. But now, we can't use the last row to obtain V3 because in the last row, it's 0 V3. So we're going to use the second row, whereby second row gives us negative 1.667 V1 minus 1 V2 minus 1 V2 minus 1.333 V3 equals to 0. So now we know that V1 is 1 because we need to normalize it. V2 is equals to 0. So we can get V3 straight away, where V3 is given as negative 1.25. Okay, so the second eigenvector is V1, which is 1, V2 is 0, and V3 is negative 1.25. All right, so remember that I mentioned there are 3 eigenvectors when 3 degree of freedom. So the same thing, in order for us to obtain the third eigenvector, we need to use lambda 3, whereby lambda 3 is 6.6226. Okay, so this is our lambda 3. And same thing again, replace lambda 3 value in the matrix of AV. Okay, in this matrix, replace lambda with lambda 3 values. Okay, and you'll get negative 2.6226, negative 1.667, 0, negative 2.5, negative 3.6226, negative 4, 0, negative 1.333, negative 2.6226, multiply with matrix V, which is V1, V2, V3 equals to 0. So same thing for lambda 1. Okay, we use first row and we're going to use the last row. First row will give us V2 value and last row will give us V3 value. So from first row, negative 2.6226 V1. Okay, remember that V1, we will normalize it to V1, minus 2.5 V2. And we don't need to write V3 because 0 V3 is 0. So why do we need to waste our time? And this is equals to 0. Okay. So since V1 is 1, so we can get V2 value straight away, whereby V2 is negative 1.05. Okay, and from the third row, it gives us negative 4 V2 minus 2.6226 V3 equals to 0. So we already have V2 value, which is this one. So replace it in there, we can get V3 equals to 1.6. So now we have already obtained V1, V2, V3. So the third eigenvector is 1, which is V1. V2 is negative 1.05, and that one is 1.6. All right, so that's all. I hope I have provided a clear explanation. Please try it yourself and see you again in the next session. Thank you.